Hi, I'm Travis, and my project was on the effects of visual scene complexity on deep reinforcement learning. So I wanted to see whether or not a really visually complex scene could affect how well an agent can learn, and the data I'm feeding the agent is actually images from the scene itself. So I wanted to see if you trained like an agent in a plain environment with like no textures, not a lot of lighting, if it would train faster, um, or if it like scores higher in performance. Um, I think this matters because most RL benchmarks they like use super minimal visuals or really complex ones, and researchers just pick one without thinking about whether that choice is like actually influencing the agent. So to do this, I built like a little basketball game. It's made with C++ and OpenGL in a library called Glitter. Glitter basically just links GLFW, GLAD, and Bullet 3, which is the physics engine I'm using. Um, and with this, I defined three different scene complexities. I have a low complexity scene that just has like flat, solid colors and minimal lighting. And then I have a medium scene that has wood and stone textures. And then a high scene that has textures for the ceiling, the floor, the walls, and then also 3 point lights. I trained a PPO agent with the CNN on each of these versions. The agent sees an 84 by 84 image from the ball's position and has to pick the right angle and power um, to score the ball. So I can just show you what the scene actually looks like. Um, so if I go into the builds and then go in here. So this is the low scene, and as you can see, I'm rendering a basketball. And in this mode, I'm not training an agent, so I can just go ahead and try to shoot. So that's what one of the scenes looks like. And then I could go ahead and do it on medium. So this is the medium scene. As you can see, there's textures applied, and then there's some point lights. And then here is the high scene. As you can see, the high scene has a lot more lighting and a little more complex textures. So those are the scenes. And then um, I'll show you a demonstration of actually training the agent. So I can run this train script and then I can feed it what environment I want the agent to run in. So let's say I want it to run in the high environment, and then I can specify the number of steps. So let's go with 500,000 steps. As you can see, the agent is training and it's shooting all these things, trying to get it in. And then I also have like a visual output. So there's the step, the episode, the success percentage, the mean reward, and then the time elapsed. As you can see, it's going through this, and then as the simulation continues to run, it's going to increase the reward, and then the score percentage should increase as well. And as you can see, every time it hits a new best score, it's going to save it, and it just saves it into the zip file. This makes sure that if it does start to regress and go down, that I do have the best version of the trained model still saved. So that was a little demonstration of that. And then I'll give you a demonstration of the results of some of the pre-trained policies I have. So we could go to demo, this demo script, and I'll put in the medium. So this RL agent was already trained, um, and as you can see, it's trying to shoot the ball from different spawn positions. I chose to do different spawn positions because it generalizes the the vision of the agent. Because if the agent was just in like a fixed spawn position, it can just memorize the exact pitch and power needed to shoot the ball into the basket, but because it's spawning from different positions, it actually has to take the 84 by 84 RGB image input and try to decide what the pitch and power will be based on that. Um, so while this plays, I'll talk a little bit about the broader impact and future work of this project. I think the main takeaway is that uh, like adding realistic visuals to an environment probably isn't going to tank your agent's performance. I found this because when I was looking into the actual results, you can see here that the overall success or the final success of the different agents based on the scene complexity wasn't that drastic. As you can see here, like the low configuration and the high configuration um, almost have like the same success percentage at the last 100. This overall success is kind of skewed because I accidentally trained the low previously, and then I used that pre-trained with my experiment script to train all the models. I had to do this because I was running out of time. But I think the last success does show like overall they reached like the same success level, and then uh, the medium agent only scored 29%, but this is probably due to variance, I think. Um, so I like going further. Some of the limitations I had were that I only ran one training seed per config. So some of the differences could just be noise. And then the task is also a single shot task, which is like simpler than most RL tasks, which have many decision making steps. Like the RL agent only has to make one decision. And then going forward, I think the most interesting thing I could do is to run this with multiple seeds to get like proper error bars and testing whether data like random crops or color jitter changes any of my findings. It'd also be interesting to make it like a sequential task, and for that I'm thinking um, based on the position, the RL agent has to actually move its camera position or the yaw of the camera to actually find where the hoop is and to distinguish it from other objects in the scene. So I would like to make the high complexity scene include multiple different objects, maybe like something blocking the shooter, and then the RL agent to first make the decision of where to configure its camera so such that it's facing towards the basket, and then the next step would be to actually shoot the ball into the basket. So yeah, that is my project. Thank you.